For 36 years, something was supposed to be there and nobody could find it. Every model said it should exist. Every comparison to the other giant planets said it had to be there. And every single attempt to actually see it had failed. Then, a space telescope built to look at galaxies, formed billions of years ago, turned its mirror toward the coldest, dimmest, most distant planet in our solar system. And it found something that, according to the physics everyone trusted, should have been too faint to detect at all. Neptune had a secret. And it had been hiding it since before most people alive today were born. This isn't speculation dressed up as mystery. The observations behind this come from NASA's James Webb Space Telescope, working with a research team led by Henrik Mellon, now at Northumbria University, alongside Heidi Hamel of the Association of Universities for Research in Astronomy and Leigh Fletcher of the University of Leicester. The findings were published in the peer-reviewed journal Nature Astronomy, backed by NASA's Goddard Space Flight Center. This is not internet speculation. This is confirmed, published science, and it rewrites something scientists thought they understood about our own solar system. Neptune has always been the planet astronomy left for last. It's the 8th planet from the Sun, over 30 times farther from it than Earth is, so distant that sunlight takes more than 4 hours to reach it. Only one spacecraft in history has ever visited, Voyager 2, on a single flyby in August 1989, and no mission has been back since. Everything humanity has learned about Neptune in the 36 years since has come from telescopes staring at it across billions of miles of empty space, trying to tease details out of a planet that shows up, even through the best instruments on Earth, as little more than a small, faint blue dot. That distance is exactly why this discovery took so long, and exactly why nobody was able to force the issue by simply looking harder. To understand why this matters, you first need to understand what an aurora actually is, because it's easy to picture the northern lights and assume every planet's version works the same way. Think of a planet's magnetic field like an invisible net wrapped around it. Charged particles streaming out from the sun get caught in that net, funneled down toward the planet's atmosphere, and when they slam into the gases up there, they release energy as light. That's an aurora. On Earth, that net is lined up fairly close to our spin axis, which is why the lights show up near the north and south poles. Scientists expected something similar everywhere else in the solar system. Jupiter has auroras at its poles. Saturn has auroras at its poles. Even Uranus, one of the strangest planets we know of, has auroras roughly near its poles. Neptune was supposed to follow the same rule. It did not. Here's the part that took 36 years to resolve. Back in 1989, NASA's Voyager 2 became the only spacecraft to ever fly past Neptune, and during that flyby, it picked up faint hints that an aurora might be happening somewhere on the planet. But a hint is not a picture. For over 3 decades, every ground-based telescope pointed at Neptune came back empty. No confirmed image, no spectrum. Nothing solid enough to publish. Jupiter, Saturn, and Uranus had all been confirmed. Neptune remained the one gap in the entire outer solar system. The missing piece nobody could close, no matter how much telescope time got thrown at it. Then, in June 2023, Webb pointed its Near-Infrared Spectrograph at Neptune, and within that single observation, something appeared that 36 years of effort had never produced. Turns out, actually imaging the auroral activity on Neptune was only possible with Webb's near-infrared sensitivity, said Mellon, the study's lead author. It was so stunning to not just see the auroras, but the detail and clarity of the signature really shocked me. In the resulting images, the aurora shows up as glowing cyan splotches layered over the planet's blue disk, unmistakable once you know what you're looking at, and completely invisible to every telescope that came before it. Now here's where it gets genuinely strange. And this is the part worth pausing on, because it's the detail that turns this from an exciting confirmation into a full-blown scientific puzzle. Neptune's magnetic field is not lined up with its rotation axis the way Earth's is. It's tilted a staggering 47 degrees off-center, discovered originally by that same Voyager 2 flyby back in 1989. To put that in perspective, imagine spinning a basketball on your finger, except the invisible magnetic net wrapped around it isn't aligned with the spin at all. It's cocked almost halfway towards sideways, like a hula hoop tilted at a steep angle around a spinning top. Because auroras form wherever that magnetic net actually connects to the atmosphere and not wherever the planet happens to be spinning, Neptune's auroras don't show up at the poles at all. They show up at the planet's mid-latitudes, roughly where South America sits on Earth's globe. Every other giant planet obeys the polar rule. Neptune breaks it completely, and now, for the first time, there's an actual image proving exactly where the light shows up instead. But the tilted magnetic field isn't even the strangest thing sitting inside this data. It's not even close. Because buried in that same spectrum, in the same few minutes of observation time, Webb picked up a second signal. one that had nothing to do with geometry and everything to do with a number that shouldn't have moved at all on a timescale this short. And once the team realized what that second signal meant, the whole 36-year mystery stopped being about where to point a telescope and started being about something happening to the planet itself. So let's pause and restack what's actually been confirmed here, because the next part of this story depends on understanding just how much stacked up before the real twist arrives. Astronomers spent 36 years unable to confirm an aurora that every model insisted should be there. When Webb finally captured it in 2023, that aurora didn't even appear where anyone expected. It showed up nowhere near Neptune's poles because of a magnetic field tilted 47 degrees off its spin axis. Two mysteries solved in one observation. But there was a third piece of data sitting inside that same set of measurements, and this is the one that turned a confirmatio N into a genuine head-scratcher for the team involved. Buried inside the same spectrum that revealed the aurora, Webb also picked up something called the trihydrogen cation, written by scientists as H3Q+. This is a molecule that shows up specifically as a byproduct of auroral activity, and it had already been confirmed as a clear signature of auroras on Jupiter, Saturn, and Uranus. H3+ has been a clear signifier on all the gas giants, Jupiter, Saturn, and Uranus, of auroral activity. And we expected to see the same on Neptune as we investigated the planet over the years with the best ground-based facilities available, explained Hamill, who leads the observation program under which this data was collected. Only with a machine like Webb have we finally gotten that confirmation. Finding H3+ wasn't the surprising part. Everyone expected it would be there eventually, once the right instrument came along. What came next is the part nobody was prepared for. Alongside the H3+ detection, the Webb data let the team measure the actual temperature at the top of Neptune's atmosphere, something that hadn't been directly measured since Voyager 2's flyby in 1989. And what they found didn't just update an old number, it rewrote the entire explanation for why Neptune's auroras had stayed hidden for 36 years in the first place. I was astonished, Mellon said. Neptune's upper atmosphere has cooled by several hundreds of degrees. In fact, the temperature in 2023 was just over half of what it was in 1989. Half. The upper layer of Neptune's atmosphere had lost roughly half of its heat over 3.5 decades, on a planet that sits more than 30 times farther from the sun than Earth does, where you'd expect almost nothing to change on a human timescale at all. That temperature drop explains everything that came before it. Auroras get their brightness from energetic collisions, charged particles slamming into atmospheric gas, releasing light in the process. A colder atmosphere means slower, less energetic particles, which means fewer and weaker collisions, which means a dimmer glow. For 36 years, astronomers had been calculating exactly how bright Neptune's aurora should be, using temperature data collected by Voyager 2 back in 1989. Every one of those calculations was built on outdated numbers, because nobody knew the atmosphere had quietly cooled by hundreds of degrees in the decades since. They weren't failing to find something that was there all along and just hard to see. They were searching for a version of Neptune's aurora that, by the time they were looking, no longer matched the planet's actual physics. According to the old numbers, an aurora this faint should have been essentially undetectable with the equipment available. Webb saw it anyway. Think about what that actually means for a second. It means every prediction made about Neptune's aurora for over 3 decades, every calculation, every failed observing run, every grant proposal built around, we should be able to see this soon, was quietly wrong the entire time, not because the science was bad, but because the planet itself had changed underneath everyone's assumptions. Nobody was chasing a ghost. They were chasing an outdated version of a moving target, and the only reason anyone figured that out is because Webb happened to be sensitive enough to catch the aurora anyway, faint as it had become, and pull an actual temperature reading out of the same data. This is the part of the story that deserves an honest pause before going any further, because it would be easy to turn cooled by hundreds of degrees into something far more dramatic than the evidence actually supports. Nobody involved in this research is claiming Neptune is undergoing some kind of runaway climate collapse, and nothing here suggests instability that threatens the planet in any way. What the data shows is a single confirmed temperature comparison between one Voyager 2 measurement in 1989 and one Webb measurement in 2023, not a continuous decades-long dataset tracking every year in between. The team themselves describe this as the beginning of a research window, not the end of one. They're now hoping to observe Neptune across a full 11-year solar cycle to understand whether this cooling is part of a regular pattern tied to the sun's own activity, a longer-term trend unique to Neptune, or something else entirely. Right now, there are 2 solid data points and a very real mystery connecting them, not a fully mapped explanation. What makes this discovery matter beyond a single planet is what it says about how little we actually understand the outer solar system in general. Every one of the 4 giant planets, Jupiter, Saturn, Uranus, Neptune now has a confirmed aurora, but Neptune was the one holding out. The missing piece keeping planetary scientists from having a complete picture of how magnetic fields, solar wind, and atmospheres interact across the entire outer solar system. There's a bigger pattern hiding underneath this too, one that goes beyond auroras entirely. Neptune and Uranus are still, even now, the two least explored planets in our solar system. Every other planet, including tiny, distant dwarf worlds like Pluto, has had a dedicated spacecraft mission built specifically to study it up close. Neptune has had exactly one flyby, lasting a matter of hours, followed by 36 years of watching from a distance. Every new piece of information about it, including this one, has to be squeezed out of instruments never designed with Neptune as their primary target. That Webb managed to resolve a mystery this old, using an observatory built mainly to study galaxies near the dawn of the universe, says as much about how starved planetary scientists have been for Neptune data as it does about how powerful the telescope itself is. There's also a question worth sitting with before we close this out. Lee Fletcher, one of the study's co-authors, pointed out that this discovery has direct implications for any future mission sent to study Uranus or Neptune up close. As we look ahead and dream of future missions to Uranus and Neptune, we now know how important it will be to have instruments tuned to the wavelengths of infrared light to continue to study the auroras, he said. This observatory has finally opened the window onto this last, previously hidden ionosphere of the giant planets. In other words, an instrument choice that might have seemed like a minor engineering detail on a future spacecraft could now determine whether an entire category of Neptune's atmosphere gets studied at all or stays hidden for another 36 years. It's worth ending where this story began. In 1989, Voyager 2 caught a fleeting hint of light on Neptune and then flew on, and ever to return, leaving behind a mystery nobody could resolve with the tools available at the time. 3.5 decades later, a telescope orbiting nearly 1 million miles from Earth, built primarily to study galaxies at the edge of the observable universe, turned its infrared eye toward that same distant, dimming planet and finally closed the loop Voyager left open. Neptune's atmosphere had grown colder and quieter in the years between those two visits, and the very thing that made its aurora harder to find is now one of the biggest open questions driving the next era of planetary science. So tell me in the comments, which part of this got you more? The fact that Neptune's auroras show up nowhere near its poles because of that 47-degree tilt, or the fact that its upper atmosphere quietly lost half its heat, and nobody noticed for 36 years.